37 seconds after a magnitude 6.0 struck eastern Samar at 6:09 in the morning Universal Time, the seismographs at Mayon Volcano, already running hot, already in mid-eruption, registered the incoming wavefront. That timing is not coincidental, and if you understand what happened at Mount Pinatubo in 1990 and 1991, the hair on the back of your neck should be standing up right now. Let's establish the operational picture because the events of the last 48 hours in the Philippines represent a convergence of geological systems that warrants serious, structured analysis, not alarm for its own sake. Analysis, because these systems are talking to each other, and what they're saying matters. Mayon Volcano, situated at 1326 degrees north latitude, 123.69 degrees east longitude on the island of Luzon, has been in continuous eruptive activity since January 6th of this year, 2026. 4 months of sustained unrest, increasing sulfur dioxide emissions, persistent volcanic earthquakes, ground deformation, inflation, deflation, the kind of oscillating pressure cycle that tells volcanologists the plumbing system beneath a volcano is actively pressurizing, lava effusion from the summit crater, rockfall hazards, ballistic fragment ejections, alert level 3 from the Philippine Institute of Volcanology and Seismology, PHIVOLCS, a level that in their classification system means a major eruption is possible within weeks, if not sooner. And the scale goes to 5. Then May 2nd happened. On May 2nd, 2026, Mayon produced its most significant eruptive event of this active cycle. Pyroclastic flows, dense, superheated mixtures of gas, ash, and fragmented volcanic rock, moving at speeds that can exceed 700 kilometers per hour, descended the slopes of the volcano. The province of Albay experienced extensive ashfall across its towns and agricultural land. Hundreds of residents were evacuated from the flanks of the mountain. Livestock and animals that could not be moved in time did not survive. Crops were damaged across the agricultural zones downwind of the summit. The imagery from that event, the lateral surge pushing outward through a side vent while the main caldera continued venting simultaneously, indicated something important about Mayon's internal structure right now. The central plumbing is pressurized enough that it is not just expressing through the summit crater, it is finding alternate pathways, lateral blowouts, flank venting. That is a system under pressure seeking release through whatever structural weakness it can locate. 48 hours later, the M6.0 struck eastern Samar at a depth of 73 kilometers, at coordinates placing it south of Mayon's position, close enough that the seismic wavefront reached the volcano within the same minute the rupture initiated. Now here is the mechanism you need to understand, because this is not speculation, this is documented geophysics. Large seismic events generate surface waves, Rayleigh waves, and love waves, that propagate outward from the rupture zone and can travel thousands of kilometers. These waves pass through everything in their path: crust, upper mantle, and critically, the fluid-saturated, partially molten zones beneath active volcanic systems. When those waves pass through a pressurized magmatic system, they temporarily alter the stress state of the system. The pore pressure in the fluid-saturated rock changes. The mechanical equilibrium that was holding a pressurized magma chamber in a locked state shifts, even fractionally. Under the right conditions, specifically when a volcanic system is already near a threshold of instability, Martin, that fractional shift can be the trigger. Sulfur dioxide flux at Mayon is currently running 2,000 to 3,000 tons per day, with spikes above that baseline. That number matters because SO2 is not stored in magma indefinitely. It exsolves from the melt as pressure decreases. High and sustained SO2 flux means magma is actively degassing near the surface. It means the system is venting from depth. And it means the magmatic pressure is not dissipating and it is maintaining because fresh material from below is replacing what degasses above. A volcano running at this SO2 output at alert level 3, having already produced pyroclastic flows, having already shown lateral flank venting, and then receiving an M6.0 seismic pulse from 73 kilometers depth to its south, is not a system we can categorize as settling down. Now let's look at the historical record. And this is where the data becomes, in precise analytical terms, extremely uncomfortable. The Philippine archipelago experiences a magnitude 7.1 earthquake in June of that year, followed 1 month later by a magnitude 7.7 in July. The July event, registering at the northern end of Luzon, is one of the most destructive earthquakes in Philippine history. It kills over 2,000 people, collapses hotels in Baguio City, and triggers landslides across the Cordillera mountain range. These two events, the 7.1 and the 7.7, occur on opposite sides of a volcanic complex that, at the time, had shown no significant eruptive activity in over 400 years. That complex was Mount Pinatubo, located at approximately 15.13 degrees north latitude, 120.35 degrees east longitude, in the Zambales Mountains of central Luzon. In April 1991, 9 months after the second of those two flanking earthquakes, Pinatubo began showing signs of reawakening: steam explosions, sulfur dioxide emissions, seismic swarms. By June 15, 1991, Mount Pinatubo produced the second largest volcanic eruption of the 20th century, a VEI 6 event. Between 10 and 100 cubic kilometers of dry rock equivalent material was ejected. The eruption column reached 35 kilometers into the atmosphere, well into the stratosphere. The sulfur dioxide injected into that upper atmospheric layer caused a measurable cooling of global average temperatures by approximately 0.5 degrees Celsius over the following 2 years. The ash clouds circled the planet. Clark Air Base, one of the largest American military installations in the Pacific, was buried and subsequently abandoned. Over 800 people died directly from the eruption. The lahars, volcanic mudflows generated when typhoon rains mixed with loose ash deposits on the volcano's flanks, continued killing people and destroying farmland for years afterward. That eruption was preceded by 2 large magnitude earthquakes on opposite sides of the volcano, within a 1-month window, approximately 1 year before the main eruptive phase. We have now documented a magnitude 6.0 event to the south of Mayon. The question that the Pinatubo precedent forces us to ask, directly and without evasion, is this: are there corresponding seismic events to the north of Mayon that we should be watching for? Because if the historical pattern is mechanistically relevant, if the geometry matters, if flanking seismic stress matters, then the northern quadrant of the zone around Mayon becomes a critical monitoring focus. Look at the seismic catalog for the Philippines from 2020 to present. The pattern that emerges when you map all M6.0 plus events is striking. There is a dense cluster to the south of Luzon, the Mindanao region, the Cotabato Basin, the Philippine Trench System, where the seismic record is continuous and intense. To the north, in the Luzon Strait Zone and the Manila Trench region, there is also documented activity. But in the central Luzon region, in the geographic band that brackets Mayon Volcano directly, there is a relative gap, a seismic quietude that stands out against the activity surrounding it. In seismology, a quiet zone in an otherwise active system is not reassuring. It can represent one of two things: either a section of fault that has been creeping aseismically, releasing stress without major ruptures, or a section of fault that is locked, accumulating strain without releasing it, which means when it does release, it will do so more violently. The seismic history of the region around Mayon's immediate latitude shows that the last significant M7.0 plus events in that specific zone occurred in the 1970s, 1980s, and 1990s, more than 25 to 50 years ago. Subduction zones do not rest, they accumulate. Now, the seismic data for the broader region since 2020 shows a magnitude 7.4 in October 2025, occurring to the south of Mayon's position, a magnitude 7.6 at a similar southern location. These are significant events, the kind that release energy and transfer stress to adjacent fault segments. When a large rupture occurs on one section of a fault system, it can increase the Coulomb stress on the adjacent locked section, moving it closer to failure. The 7.4 and 7.6 to the south, followed now by a 6.0 beginning to populate the quieter zone closer to Mayon. This is a stress migration pattern that warrants attention. Now let's bring in the solar dimension, because this is where the analysis becomes more complex, and where intellectual honesty requires us to be very precise about what we know and what remains scientifically contested. Solar activity influences Earth through several documented pathways. The solar wind, a continuous stream of charged particles emanating from the sun's corona, interacts with Earth's magnetosphere, compressing it on the day side and extending it into a long magnetotail on the night side. When the solar wind is disturbed by a coronal mass ejection, by a high-speed stream from a coronal hole, or by the impact of a solar flare's associated radiation, it drives geomagnetic storms. During geomagnetic storms, Earth's magnetic field oscillates. Rapid field variations generate geomagnetically induced currents in conductive structures, pipelines, power grids, the ocean, and theoretically the conductive rocks of Earth's crust and upper mantle. Whether those geomagnetically induced currents are sufficient in magnitude to influence seismic or volcanic systems remains a subject of active scientific debate. There are peer-reviewed papers arguing for statistical correlations between geomagnetic disturbances and seismic event clustering. There are equally rigorous papers arguing the correlations are not robust when properly controlled. The mainstream consensus in seismology does not regard solar activity as a primary or reliable driver of earthquakes. We hold that position clearly. What we can observe is this: a coronal hole, a region of the sun's corona where the magnetic field opens outward into space rather than looping back, allowing plasma to escape as a high-speed solar wind stream, is currently positioned along the solar equator. When a large equatorial coronal hole faces Earth, the high-speed solar wind stream it produces can impact Earth's magnetosphere with enough energy to drive minor to moderate geomagnetic disturbances. That stream is arriving within the next 48 to 72 hours, And then there is the M1.89 class solar flare that fired today, the strongest solar flare in the past week at minimum, possibly longer. The Philippine M6.0 earthquake registered at 6:09 Universal Time. The M189 flare peaked approximately 4.5 hours prior. The temporal proximity is noted. It is not proof of causation. But the correlation, in the context of everything else we are observing, belongs in the analytical record. The broader solar cycle context matters here because it directly parallels the Pinatubo period. Pinatubo's 1991 eruption occurred during solar cycle 22, near solar maximum, a period of peak solar activity as measured by sunspot number. We are currently in solar cycle 25, which has proven stronger than its predecessor, solar cycle 24, and is now transitioning from maximum toward the descending phase. The solar activity levels are not identical to 1991, but we are in the same general phase of the cycle, elevated, sustained solar output, with coronal hole activity that has been persistent and significant throughout 2024, 2025, and now into 2026. Large, long-lived coronal holes rotating across the solar equator, continuously buffeting Earth with structured solar wind, a leading wall of high-density solar wind followed by a high-speed, low-density trailing stream that compresses Earth's magnetosphere and drives geomagnetic variation. Whether this is mechanistically connected to the geological activity in the Philippines or not, the operational picture it creates is one of layered, concurrent energetic inputs to an already stressed geological system. Let's return to Mayon and close with a precise risk assessment. Mayon Volcano is currently the most carefully monitored volcanic system in the Philippines, and for good reason. It is one of the most historically active volcanoes in Southeast Asia, with over 50 documented eruptions in recorded history. Its 1814 eruption buried the town of Cagsawa under pyroclastic flow, leaving only the church bell tower visible, a landmark that still exists at approximately 1314 degrees north latitude, 123.68 degrees east longitude, and serves as a permanent memorial to what this volcano is capable of. The current eruptive cycle, running since January 6, 2026, shows no clear signs of approaching termination. Sulfur dioxide flux is sustained. Ground deformation continues. The pyroclastic events of May 2nd introduced lateral flank venting that indicates increasing internal pressure, and the M6.0 of eastern Samar has now introduced a seismic perturbation to an already destabilized system. The most probable outcome, statistically based on Mayon's historical behavior, is that this cycle continues in its current mode. Episodic effusion, periodic pyroclastic flows, sustained degassing, without escalating to a catastrophic eruption. Mayon has cycled through elevated alert phases multiple times in its modern monitoring history, without producing a VEI-5 or VEI-6 event. That history is real, and it matters. But the conditions that would need to be present for an escalation toward a Pinatubo scale event, sustained high SO2 flux, lateral structural destabilization, seismic stress input from nearby large magnitude events, are not absent from the current picture. They are present, not all of them at the levels that would indicate imminent catastrophe, but present. The specific threshold to watch, the indicator that would warrant a significant escalation in concern, is this. If M7.0 plus seismic events begin to register in the fault segments north of Mayon's current latitude, in the zone that remains seismically quieter than the surrounding regions, two large, flanking earthquakes, north and south, within a compressed time window, that is the Pinatubo geometry. That is the pattern that preceded the second largest volcanic eruption of the 20th century by approximately 1 year. We have the southern event, a 6.0, not a 7.0, but the progression matters. A 6.0 populating a previously quiet zone, following a 7.4 further to the south. The energy is migrating, the stress is transferring. Whether it migrates far enough, fast enough to produce a flanking rupture to the north of Mayon before the volcano's own eruptive cycle reaches a critical threshold, that is the question that cannot be answered from current data. What can be answered is this. The people living on the flanks of Mayon Volcano, the agricultural communities of Albay Province, the coastal populations within tsunami risk corridors if a major collapse event were to occur, they need accurate, timely, and precise information. Not sensationalism, not false reassurance, accurate information. 5LCS is doing that work. The Alert Level 3 designation is not bureaucratic formality. It is a signal with operational consequences. Evacuation framework activation, exclusion zone enforcement, continuous monitoring escalation. The institutional systems are running, but institutional systems respond to events that have already occurred. The analytical framework we're building here is designed to watch for what hasn't happened yet. And right now, the data points we're tracking, the sustained Mayon eruptive cycle, the M6.0 seismic input, the seismic gap to the north, the solar energetic environment, the historical Pinatubo parallel, are converging in a way that does not allow for comfortable dismissal. Watch the northern seismic zone, Watch the SO2 flux numbers at Mayon for any sustained spike above baseline. Watch the coronal hole stream arrival in the next 48 to 72 hours and whether it correlates with any additional seismic activity in the Philippine subduction system. And consider the question that the Pinatubo record leaves permanently open. If a volcano that showed no significant eruption in 4 centuries could produce the second most powerful eruption of the 20th century, triggered in part by 2 flanking earthquakes within a 1-month window, what does a volcano that is already erupting, already at alert level 3, already producing pyroclastic flows? What does it do when the second flanking earthquake arrives? We are watching for that answer in real time, and the next significant seismic event in the northern Luzon zone will tell us more about the trajectory of this situation than anything else currently in the dataset. Stay on this.